So let me begin by thanking the organizers for giving me this opportunity to talk about my work. So I'm going to talk about the recent advances in worm inflation from cosmic microwave background to primordial black hole. And this talk is based on a series of work I have carried out during my PhD, postdoc, and currently I'm pursuing. Okay. So as my previous speaker Suratna has already introduced and motivated worm inflation, so I'll just brush through this slide. But yeah, so some key points about this, the difference between cold and warm is that in cold inflation, the universe attains a supercooled state after this exponential expansion. And there is a separate preheating phase at the end, which then again brings back temperature in the universe. Okay. But in warm inflation, there is a production of particles. So throughout this inflationary phase, so inflaton has couplings and it dissipates into these particles throughout this inflationary phase. So you do not require a separate preheating phase at the end. Okay. The equation of motion of inflaton is modified with the additional dissipation term we have already seen in the previous talk. Okay. And this concept was just 15 years after the inception of inflation. Okay. So some of the motivations are already talked about by Suratna. So it's a more, so warm inflation is a general description. Okay. It is more appropriate to consider the couplings. We should not neglect if there are even slight couplings of inflaton with the other fields, that should be considered. So it should not be ad hocly avoided at the first place. Then a reheating phase might not be needed at the end of inflation, that's another point. Then there are certain models of cold inflation, very easy ones like the monomial quartic potentials, which are already ruled out in the cold description, but warm inflation can accommodate those models by lowering this tensor to scalar ratio. Then there are studies which show that warm inflation can also lead to non-Gaussianities. Okay, and in future if we have some detections of non-Gaussianity, that can be a test of these warm inflationary models. Okay, then there was a eta problem discussion that the steeper potentials of inflation can also be accommodated in this warm description. So you don't require a very flat potential, even steeper potentials with inflaton coupled with the other fields, that can be also viable with this warm description. Okay. Then there are some conjectures from some high energy theories or UV complete theories, which are Swampline and Transplanckian. I'll talk about it. So even these type of conjectures which can help inflation to embed into some UV complete theory, these are also favorable with the warm inflation models. Okay. And the very important point about warm inflation is that it naturally leads to some features at the small scales which were not explored earlier, but we in our studies have seen that there are some natural mechanisms only that dissipation can lead to the formation of primordial black holes at the very small scales. Okay. So the background dissipation, okay, the background equation of inflaton is modified with this additional friction term, okay, and this upsilon is the dissipation coefficient, which depends on how this inflaton is coupled. Okay, when we can just reparameterize our equation in terms of another parameter q, which is the ratio of the two friction terms, which one dominates, decides which regime of inflation. I mean, if q is more than 1, we can say it's just a nomenclature to say that the dissipation is more and we are in the strong dissipation regime, and if q is less than 1, so we are in the weak dissipation regime, and in the limiting case when q is 0, we retain what is the standard cold description, the cold inflation. Okay, so how is this upsilon obtained? So it depends on how inflaton couples. So it's solely a function of the field value and temperature, and it depends only on the Lagrangian which we put into while we describe this process of coupling of inflaton. Okay. So there are some motivations of deriving these forms of epsilons in literature. So some common forms are that it's t cube by phi square, it's linearly, so it's only a function of t and phi, okay. There are different forms which are like they are in, so these two forms are in the supersymmetric inflation models. So we have an inflaton and it is undergoing a two-stage decay mechanism. So it is coupled with some intermediate fields and those fields are then going into radiation. So in the two-stage decay mechanism in these SUSY models, we have two limits, one where we get this t cube by phi square kind of a form and the second where we get a linear kind of a form. Okay, and there is also a warm little inflation model, okay, which is recently proposed in 2016. So extra gauge symmetries are added in the inflaton potential so that the thermal corrections are controlled. Okay. Then there is another form t cube by m square, which is a minimal axion, minimal inflation model, where this inflaton is an axion and it has some couplings to the non-abelian gauge fields, and these are recently introduced in 2019. Okay. So the form of primordial power spectrum in warm inflation is modified with the both thermal and quantum fluctuations, and it's given like this. So the first term resembles the standard cold formula we know, and there is additional square term which has contributions because of this T by H, these thermal corrections, thermal noise contribution. Okay, and somebody asked previously that what is the hierarchy of T by H. So this T is always greater than H in warm inflation. So this term is contributing definitely for warm inflation. If you are dealing with a high dissipation, so this is the most dominant one. Okay, okay. The N represents, so inflaton field itself can be excited from its vacuum state. So there can be a non-zero thermal distribution for inflaton, okay, which is basically this inflaton distribution function, which is considered as a Bose-Einstein distribution. Then the radiation fluctuations can have a feedback in inflaton fluctuations, which can lead to the growth in spectrum, which is encoded with this growth function GQ. It is obtained numerically by solving the coupled inflaton radiation fluctuation equations, and for a linear, it's only a function of temperature, it's independent of phi. So if you have a linear dependence on temperature, the growth is like this, and if it's kind of a cubic dependence, the growth is like this. This is very crucial factor when we are dealing with a strong dissipation regime and when we are dealing at the small scales, because you can see it's a huge power of Q, right? And if Q is a big number, this term is going to dominate a lot. I'll come to it again in next slides. Okay, so in our initial studies, we did CMB analysis of a monomial potential with two forms of epsilons, okay, and we found that there is a, okay, on the x-axis is the value of this dissipation parameter at the pivot scale. Okay, so pivot scale means the CMB, the 0.05 megaparsec inverse scale. Okay, so we can see that this T cube by phi square can accommodate only a weak dissipation regime to start with. Okay, but a linear T can accommodate both. By accommodation, I mean that this NS is consistent with the predicted NS of this model is consistent with the Planck results. Okay. So we have both strong and weak dissipation regime possible for a linear T. And the R values, the tensor to scalar ratio values, you can see that depending on the value of Q, we have a lower tensor to scalar ratio. So that means these models can be consistent with the Planck observations. Okay. Okay, so this is how the standard power law parameterization in cold inflation looks, the black line. AS k to the power ns minus 1, that's the standard cold inflationary spectra, and these are the lines which show that in warm inflation, if you have even to begin with a very small dissipation, you can have a sufficiently differing spectrum. Okay, So we see that the inflaton rolls down this potential. To start with, we had a very low value of dissipation parameter, but as inflation proceeds, you see that this parameter increases. Okay. So this is a very crucial point about this model, that it leads to a huge evolution, a huge growth in Q value. Okay, the T cube by phi square and this lambda phi 4 potential with T cube by phi square. It leads to huge enhancement in the value of Q in this inflationary model. Okay, and because the power spectrum I showed is dependent on the growth function, it would be hugely enhanced. Okay, so this is what we explored in our next study, which was on primordial black holes. Okay, so but what are black holes? So primordial black holes are those with primordial origin. Okay, they are different from astrophysical black holes, which are stellar end products. They have different formation mechanism. Okay, they can be formed by collapse of overdensities. They can form very early in the universe. Okay, in the radiation era itself. Okay, so there are a lot of studies in this primordial black hole after the detection of this LIGO gravitational waves. There is a surge in studies on PBH. Okay, we'll be listening to more of PBH by Rajiv in his talk tomorrow. But okay, so I'm showing here how much abundant black hole can have, depending on the mass of black hole, its abundance is restricted from various observations. So if there are black holes, why can't we see? So there are different constraints from different observations. Okay, so black holes with less than 10 to the power 15 gram mass, these are bound. Their abundance is bound from evaporation constraints, because they would have evaporated by today, whereas 10 to the power 15 grams and higher masses would have implications in gravitational lensing or some other phenomena. So their bounds are from other experiments. But there is this quantity which is basically the fraction of black hole in dark matter. Okay, so if black holes are stable and they are there in the universe, so that they can constitute the dark matter. So there are constraints on their abundance or on their fraction through different experiments. Okay, and there is a window in which there are no constraints to rule them as the total dark matter. So for the first model, lambda phi 4 and T cube by phi square, when we extrapolated our power spectrum for the small scales, we saw that there is a natural, because the dissipation parameter is growing very large, that's why the growth factor is contributing and the power spectrum is getting enhanced naturally. This is not imposed in the potential or in the spectrum itself, it is coming as a natural effect. Okay, this was seen for the first time in this paper. Okay, and the abundance of these, okay, so we see that nearly a kilogram mass, tiny mass black holes are being formed in this model of inflation, and the abundance of these are restricted because of their evaporation constraints. Okay, but if these evaporation ceases at some point, so these are tiny black holes, they are evaporating fast, but if we seize this mechanism at some scale, some Planck scale, then the remnants of these products of these Planck mass can be a dark matter. This is one proposal in a Nature paper by McGibbon. Okay, so we see that possibility here also. Then there are, okay, so associated with the scalar perturbations, large scalar perturbations also source the tensor perturbations at second order. Okay, so this leads to a spectrum of scalar induced gravitational waves. Okay, and we see that associated with these tiny black holes, we have a spectrum of gravitational waves of very high frequency. Okay, this is in this work by So next we explored that whether there is a possibility that we make the dark matter. We obtain tiny black holes, but can we make black holes in the range which is possible for the full dark matter, the unexplored window. So here we considered another model, a non-canonical worm inflation. Okay, we had this additional G type term, worm Higgs G inflation. Okay, so G symmetry is there in this term, and we considered a linear dissipation coefficient. So again, we see that there is an enhancement in the power spectrum, but at the intermediate scales, not at the last small scales, but the intermediate scales, which correspond to PBH in this unexplored window. Okay, so we have a possibility that the PBH formed in this model can constitute the total dark matter abundance. Okay. And the associated gravitational wave spectra of these lie in the sensitivity of LISA, VBO, DESICO. Okay. Then, because inflation is a low energy theory, we need to embed it in some UV complete theory, which is done via some conjectures from string theory, which are Swampline and Trans-Planckian conjectures, which favor that we have a sub-Planckian excursion for this. So there are three conjectures: distance, de Sitter, Trans-Planckian. So we require that inflaton evolution is sub-Planckian, okay, and the slope of this potential is greater, which is not allowed with the cold inflation. Okay, so standard cold inflation is not in agreement with these conjectures. However, we can accommodate these in our warm inflation model. That is what we show here. So because there is a coupling of inflaton with the fields, it can have a sub-Planckian excursion, but still continue to have that 60 e-folds. Even if it starts at a lower value of field and it moves very slowly, it can continue for 60 e-folds to have sub-Planckian excursion, but still attaining that 60 e-folds. The other is basically the steepness of the potential is also, a steeper potential is also allowed in warm inflation. Because it is coupled, so it won't roll down fast. There is a coupling which restricts its motion as a friction term. So it can have a motion on a steeper potential, but still favoring this Swampline conjecture. Okay. Then the third one is Trans-Planckian censorship conjecture, which is related with the scale of inflation and which is also related with the density scaling. Here, this conjecture proposes that the density scaling is extremely less. So currently I'm pursuing this project, which is with my students, and we are considering again a variety of possibilities, but now we are considering two parameters instead of just one. First is input, so only that this is this study can allow for some solution. But the problem with this study is that it only gives you the less input method as many number of inputs included to measure how strong inflation is acting. But this evidence is so what we propose is that if this initial phase is dominated with this study and then there is a subsequent phase, which will naturally come because as the phases between time goes down, so this second time automatically comes to that phase. We see that the second phase will have a different spectrum. That's the motivation, and combined if we see the power spectrum in different phases. So considering that the 40 e-folds are covered in first phase and some 10 e-folds are covered in the second phase, or satisfying the complete maximum numbers, we see that we can be compatible with the ACT results. We can start with a strong dissipation regime, okay, and we can also have a sub-Planckian field excursion. That means Swampline conjectures are also allowed. Okay, so now what would be the PBH signatures of these models is what we are ongoing at present. Okay, so this is the summary of my talk. I leave it for you to read and can ask questions if there. Thank you.
Thanks, teacher, also for keeping in time. Questions? Sure.
Can you go to slide 10, please?
Yeah.
What happens to K? Where is the K end?
Okay, so K end is basically the points here. I mean, whatever model you are considering, this endpoint is the K end. We are exploring the full 50 or 60
What
e-folds.
will happen beyond Kn? Have you evaluated the spectrum beyond Kn?
No, beyond Kn, what would it mean? Like the
What it means?
inflation
What
has
it means?
hence
I can evolve the spectrum and evaluate it.
No, but that's the smallest scale which is exiting the horizon in
I can
inflationary
evaluate it.
era.
You should do that. Okay, so I will let you do that. You should evaluate. Modes are still there.
Modes are still there, but those who have never exited are never considered. I don't think it's
Exactly. People don't consider it, but you should. Okay, you should examine what happens to them. Number one, because I would like to see what is the nature of the spectrum on those scales.
okay.
Now, I mean, you have used the expression that you had earlier for the power spectrum to arrive at this power spectrum,
Yeah.
the analytical one.
Yes.
I mean, typically in cold inflation, such features, strong features will arise. There are slow roll. There are deviations from slow roll. Are there constraints under which your spectrum has been derived, analytical one? Are those constraints valid for such scenarios?
So we are still obeying the slow roll. We are not violating slow roll anywhere. This is inflation with slow roll, but with modified
So
slow
whether
roll.
the slow roll parameters themselves are enough, I am not sure when there is an additional field involved.
No, but see,
So
the presence
I
of
don't-
other fields leads to this Q term. The Q is basically the ratio of epsilon. Epsilon has that interactions with the other fields, right? So the slow roll conditions are modified. Like epsilon is not no longer needed to be less than 1. Instead, it can be less than 1 plus Q. So that information is there in the Q. So slow roll conditions are modified considering its couplings.
Because it's often very difficult, you need strong deviations from slow roll in inflation to generate blue spectra.
Yes, that's a difference.
So I was a little surprised in your latest slide that you are unhappy with the red spectra. Okay, we'll talk over coffee.
Yes, sure.
Okay, go ahead, please.
So, during warm inflation, the radiation must be subdominant with respect to the scalar field, right?
Yes.
So, we cannot get the radiation era immediately after the end of inflation. There is some other epoch between inflation and radiation era, right?
It depends on model. So for lambda phi 4 model, I have it in my paper, if you see that if you evolve rho phi and rho r, there is a mismatch, like rho phi is still dominant at the end. So a little bit phase of reheating might be needed. But there are models, like there are some papers which have some models which like end inflation when rho r takes over rho phi.
So, what is the signature of that era on the primordial gravitational waves?
We haven't explored that era. We have just considered inflationary scenario in this study at least.
Okay.
Yeah, that aspect which you are saying is significant, and yeah, that needs to be explored.
Thank you.
Yeah, I have one question. So
Yeah.
I always had this question in mind when I had seen your paper.
Yeah.
The thing is that you have a flat spectrum for the CMB scales, and suddenly it rises up,
Not
right?
suddenly, it took so many e-folds and so many.
But then it rises up,
it
right?
rises up. Yes.
But is this a fine tuning?
No, it's not fine tuning.
So then how can you keep us? I mean, there should be some upper limit on Q or something that will let your spectrum to be very flat for the CMB scales, and then slowly rise up, or whatever is the rate of that
We
rise.
started with a pivot value of Q.
Yeah.
Then we have a condition that when we can end inflation, the inflation will end when our slow roll parameters are disobeyed. Okay, so
That's
we
right.
consider eta parameter because that is more in comparison with epsilon. Okay, so we know the end point also from that condition of eta equal to 1 plus q, and eta is basically 1 at 1 plus q, right? We have expression for eta in terms of potential parameters, and this is equal to 1 plus q. This gives a upper bound on q. So we start with a q pivot, we have a q end. In between, it is evolving. It's not fine tuning, it's slow roll only. There is a dq by dn expression, right? You showed
Yes.
it. So dq by dn governs how this q will go from this point to this end point. Only this dq by dn is enough. There is no other thing required for knowing how it will evolve. And if q evolves, so correspondingly gq will evolve, and correspondingly the power spectrum will evolve.
So I always doubted that it leaves the CMB scales intact. It only affects the scales which are not seen in CMB.
But it's natural process. It's not because Q is enhancing.
That I think the physics behind it needs to
That
be
physics
explored.
behind is basically governing the. There is a dq by dn, right? You know, it's not a
Yes.
constant in these models.
That's right. So
Whenever
there are even warm inflationary models where dq by dn decreases.
decreases.
And
right?
then
But
you
this
will not-
model, this model has a enhancing Q, and that is the crucial point why spectrum increases. The other models which have a decreasing Q might lead to a suppression in the power. So it is equally possible there can be a suppression. For other models where if it is required, we can explore that. But for PBH, we require a high power spectrum value. So this was the motivation to
Okay,
continue it.
we'll talk.
Sure,
later.
we can talk.
Okay, so I think at the beginning somewhere you mentioned maybe you are saying that temperature is greater than the
Hubble.
Hubble parameter. Is this during inflation?
During warm inflation, yes.
How do you make sure the temperature is greater than Hubble parameter? Typically, your H square, if the background is thermalized, your energy density is T to the power 4. Now,
Yes,
H square
yes.
is T to the power 4. And how your T is greater than H? And
Okay.
how do you maintain that?
Okay, so we don't, okay, yeah, that's a point which is not, okay, so T by H has to be greater than 1 so that these equations hold. Otherwise, there is no point. If this is less than 1, then it's the standard cold thing.
Standard. Yes.
Yeah.
Yes,
So-
that is my question is how do you get T is greater
So
than
Q
40?
decides actually for different Q values, the dissipation parameter decides that we achieve that condition.